So, we will start with a few examples. So, let me start with example number 1. Okay, we will go through it somewhat quickly. If you have any doubts or questions, please remember to contact Mr. Tony and ask during the interactive session. So, first one, we are given the x of n as a sequence 1, 3, 4, minus 2 and 5, okay, and this is my origin. 1, 3, 4, minus 2 and 5. Okay. We are asked to calculate, the first thing that we are asked to calculate is the output of this operation. Downsample by a factor of 2 followed by upsample by a factor of 3. Okay. So, this is x of n. We want to know what is y of n, the output of this operation, okay, y of n, and there is an intermediate after. So, in all of these cases it is advisable for you to define an intermediate sequence so that we can calculate the intermediate sequence and then do the final operation. So, what is x1 of n? The sequence. So, starts at the origin. So, the sample, that sample is retained, next sample is removed, the following sample is retained. So, 4, 5, the minus 2 got replaced and dropped, and then there are zeros beyond that. On this side 3 is dropped, 1 is present, okay, and then there are zeros. So, this is the sequence, that is x1 in the intermediate sequence. Always mark the origin so that we do not get confused. So, only 3 non-zero samples, 1, 4 and 5, the 2 samples got dropped because of the operation. Now, what is the output? Let us call that as y1 of n. y1 of n starts with the 0 valued sample, which is at 4, and then upsamples by a factor of 3. That means inserts n minus 1 zeros, in this case 2 zeros. So, 4, 0, 0, 5 and then zeros. Similarly, it is 1, 0, 0 and then zeros before that. Okay, so, this is the sequence that came at the output of this operation, downsampling by factor of 2, upsampling, and the origin continues to remain at the same point. Always that origin, when you do the sampling change, keep n equal to 0 as the fixed reference. Okay. Now, second example that I would like you to do is x of n upsampled by a factor of 3, downsampled by a factor of 2, downsampled by a factor of 2. Okay, we will call this the same input sequence, we will call the output sequence now as y2 of n, the intermediate sequence as x2 of n. Okay, please write down what the sequence x2 of n is, upsampling by a factor of 3. So, basically it will be original sequence, not the ones that we have written above. 4 is my midpoint, 2 zeros followed by minus 2 followed by 2 zeros followed by 5 and then zeros. On this side it will be 3, 0, 0, 1, 0, 0, 3 and then zeros prior, and origin is at 4. This is the sequence that comes with the upsampling, followed by the downsampling. Y2 of n, you start with sample number 4, okay, retain every second sample, then first 0 is thrown away, the second 0 is retained, the 2 is thrown away, the next sample, next 0 is retained, the 0 is thrown away, 5 is retained, and so on. Okay. And on this side similarly, the first immediately after 4 to the left, that sample is thrown, the next one after that is retained, 3 is dropped, the one after that is a 0 is retained, and then there is 1 and then there is. So, you can see that this is the sequence that was obtained as y2 of n. Okay, look at y1 of n and y2 of n. Origin is still at 4. You will agree that y2 of n is equal to y1 of n. Okay, and that's what comes out to be as the observation. Now, I would like you to go through this exercise one more time with a slight difference. So, this time around, same sequence x of n, upsampled by a factor of 2, or let us start with downsampled by a factor of 2, upsampled by a factor of 2, same, not 3, right, no, both times. So, this is y3 of n, this output is y3 of n, and then you have x of n upsampled first by a factor of 2, downsampled by a factor of 2, and this is x of n, output is y4 of n. Okay. So, what you will find, please go through the process of calculation. I will just write down the final answer. y3 of n is the sequence which is given as follows. Okay, we have 0, 1, 0, 4, 0, 5, 0, dot dot dot. Okay, that is the sequence. Please do verify that you are getting that as your expression, and this is the origin. And then y4, very interesting, is a sequence which is given by zeros 1, 3, 4, -2, 5, 0, 0, 0. This is the origin. Please verify that y4 of n is equal to x of n, and also y3 of n is not equal to y4 of n. These two blocks did not produce the same output. They look very similar to the previous case. So, this leads us to two important results which you must always keep in mind. Okay, important results. The first one is given as follows. Any time you take a sequence and upsample by a factor of n, and after which you downsample by a factor of n, same value. Okay, this output y of n will be equal to x of n, guaranteed. Why? Because upsampling by a factor of n, you inserted n minus 1 zeros, and then the next sample arrived. Downsampling, you removed n minus 1 samples. Anyway, you already inserted n minus 1 zeros. Whatever zeros you inserted, you have removed, and therefore you will get back the original sequence. Okay. The second result, x of n, if you upsample by a factor of n and then downsample by a factor of m. Okay. Now, comparing this with the same input, first you downsample by a factor of m, upsample by a factor of n. Okay, let us call this output as y1 of n, this output as y2 of n, same input to both. Okay, x of n to both, y1 of n, this is y2 of n. Okay. The result is y1 of n is equal to y2 of n if and only if n and m are relatively prime. Okay. So, for example, 2 and 3 2 is a prime number, 3 is a prime number, so therefore and they are relatively prime, no common factors. So that is why you were able to get the same answer when you did downsampling by 2, upsampling by 3, and then you interchange the order, you got the same value. Okay. Now here is a very important result. So take the first operation, what we did as the first operation. This operation okay, let me copy paste that. Okay, this operation is not equal to, okay, this is not equal to the, because they are not relatively prime, right? Both are the same value, n and n. So this will not satisfy. So if you do downsampling by a factor of n followed by upsampling by a factor of n, you will get a different sequence. Okay, and very important, y of n, this sequence will be y, if you call this as y3 of n, and this as y4 of n, y3 of n will not be equal to y4 of n. Okay, important result to keep in mind, and the reason is that these two blocks can be interchanged if and only if n and m are relatively prime. Okay. So I hope you are comfortable with this. Take your time, look through these examples, and then make sure that you are comfortable with these results. And if there are any questions, please remember to discuss them during the interactive session. Let's move on. Couple of more examples. So this is example 2. The first example was all about upsampling and downsampling. This is example 2. Again, you have done several examples in your assignment. I just wanted you to think about this one more time. Okay, I have a sequence x1 of n which is periodic with period n1. Periodic with period n1. Okay, x2 of n is periodic with period n2. Okay, and we want to know if x1 of n multiplied by x2 of n is periodic. Okay, in your assignment you have looked at sum of two periodic sequences. Now I am asking you the product of two periodic sequences. Is x1 of n, is this periodic? Okay, question mark. Okay, if it is periodic, if periodic with period equal to n, uppercase n, with period equal to n, then it should satisfy the following properties. X of n is equal to x1 of n times x2 of n. Okay, so x of n plus uppercase n, period, will be equal to x1 of n plus n multiplied by x2 of n plus n. Correct? Now, if it is periodic, then this must be equal to x1 of n and this must be equal to x2 of n. In that case, then the product of these will be equal to x of n under this condition. So, for this to be true, what do you need? You need n to be equal to what is, it is x1 is periodic with a period equal to n1, but any multiple, some multiple of n1, right, some integer multiple of n1 should be this, should satisfy. Therefore, x1 will come out to be x1 of n will be come out to be. Similarly, x2 of n, this will be is also periodic, but it has got period n2. So n must be some multiple of n2. Okay, exactly the same reasoning that you used for the sum of two signals is what we are using here as well. Okay, so we can write it down in the following form: x of n plus n is equal to x1 of n plus Pn1, which is periodic. So therefore, this will be equal to x1 of n. This will be equal to x2 of n plus qn2. And what do we have from this particular step? We have n equal to Pn1 equal to Qn2. Okay. So which then says if I take the ratio n1 by n2, this will be equal to Q by P. Okay, I take n1 and n2, reduce it to a rational form Q by P, where Q and P are integers, and the period will be equal to n will be equal to P times n1 will be equal to Q times n2. Okay, that is the operation. Now here is the example or application of this particular. So application. Okay, we are given an example. In this example, n1, that is the period of x1, is equal to 90. n2, the period of x2, is given to be 54. Now I want to know what is the period of the product of these two periodic sequences. So simple, we say, okay, write down n1 by n2, that will be equal to 90 by 54. Go ahead and simplify, it will come out to be 5 divided by 3. Okay, remember that this is Q, this is P, this is N1, this is N2. So the period can be P times N1, which is 270. It can also be given as Q times N2. Obviously both should give you the same answer, that was 270. So this particular sequence for this set of values, x1 of n, x2 of n, will be periodic with period n equal to 270. Please add this to the set of concepts that you have looked at in the context of the periodic sequences. You looked at sum of sequences. You can also look at any general product of sequences. I know that in the assignment you have a cosine product of two sinusoidal functions. Product of two sinusoidal functions you can simplify as sum of two sinusoidal functions, right? Cos A, cos B, you can write it as sum of two trigonometric functions. So there you use the addition of periodic sequences. Now x1, x2 are not sinusoidal functions, so you cannot simplify it as sum of two functions. So therefore, good for you to have this as a tool also for you to work with. All right. So let us keep looking at some of the one more set of examples which will be helpful to reinforce the concepts that we have studied so far. Okay, the first thing is about periodic sequences. Okay, I am going to ask you about periodic sequences. Is U of n periodic? Is U of n periodic? Okay. What is U of n? U of n, unit step function. It has a value 1 at n equal to 0, then value 1 for all positive values. Okay, and this is 0, 1, 2, all the way to infinity. So this is n. Okay, this looks like a periodic function, right? It looks like. However, a period, and what is the period? You sort of see that the sample is repeating with a period equal to 1. So now basically if you look at the negative side, okay, U of n plus 1. So not U of n. So what is the signal at this point? The signal at this point, okay, a periodic signal must go from minus infinity to infinity. So basically it must be repetitive over the entire range. What you find is the U of n is a periodic signal with period n equal to 1, but only for n greater than 0. The minute you go to the negative side, the periodicity is lost because it becomes 0. So this particular signal it looks periodic, but it is not, because it does not satisfy. So, for example, u of n plus n, is it equal to u of n? This is a test, right? This is the test, and we said that the period looks like n equal to 1. Okay, so basically, if you look at let us say u of n plus 2, u of n plus 2, some shifted version of the period, the sample, then let me see, u of n plus 2, whether it is equal to u of n, no, this you have to be careful with this. Okay, the sequence u of n, okay, yes, correct. So let us test it for let us test it for some values. Okay, u of, let's start from n equal to 0. N equal to 0 plus 1, is this equal to u of 0? Correct. Yeah, u of 1 will be okay. So then, by the way, don't treat this as a unit step function, but as a function whose value. So let me just let me call this as some x of n. Okay, this is some x of n which looks like this. So x of plus 1 is the same as x of 0. Okay. Similarly, if you take n equal to 1, x of 1 plus 1 is equal to x of 1. Fine. Now, this is where the problem will come when you say x, what about minus 2, n equal to minus 2. So, x of minus 2 plus 1 is minus 1 is equal to, is it equal to x of, what is that, n, x of minus 2. Wow, fine, correct, yeah. But what about n equal to minus 1, x of 0, is it coming out to be 0, minus 1 plus 1 will be 0, is it equal to x of minus 1? No, right. So, this is where the periodicity will break down. So, basically this is, you have to be very careful in applying the evaluation of periodicity. A periodic function is something that will go from minus infinity to infinity. So, that is something that you must keep in mind. Okay, now comes a interesting application of this. X of n, x1 of n, a new sequence, I am going to define it to be u of n plus u of minus n. Okay, if it is a one-sided sequence, it is not periodic, I am making it a two-sided sequence. Okay, is this periodic? Verify. This is a signal which starts at n equal to 0, has non-zero values. This is u of n. Okay, dot. These are 0 valued samples here, and the other one is just a flipped version. So, you have a sample here and then dot. Okay, and it's 0 valued samples on the right hand side. Okay, is this function periodic? Add these two functions, what do you get? You get a signal that has got a value equal to 2 at the origin, 1 everywhere else. It is 1, 1, 1 on this side, 1, 1, 1 on this side. So, basically a height of 1, this is at 0, 1, 2, 3, minus 1, minus 2, minus 3. Okay. So, the sum of these two is this value. Okay. So, this is the sum of these two sequences. This is not periodic. Okay. This is not periodic because it is not something that is repeating. The sample number 2 occurs once and does not occur anywhere else. So, this is not a periodic function. Okay. Now, before you get convinced that these type of things are not periodic, look at this particular x2 of n is equal to u of n plus u of minus n plus 1. Sorry, u of minus n minus 1. u of n minus 1, n minus n minus 1. Okay, u of n, you know what it is. What is u of minus n minus 1? Always do it with the shift first and then followed by, so u of n minus 1 is given like this. This is how u of n minus 1 looks like. It starts out at n equal to 1, 2. Okay, this is what you have as the sequence u of n minus 1. And so u of minus n minus 1, u of minus n minus 1 is a mirror image of this. It will start at n equal to minus 1, minus 2, minus 3 and so on, minus 1, minus 2, minus 3, and this is all on this side. On this side it will have 0 valued samples. Now if you add this sequence to u of n, what do you get? x2 of n looks like this. This combination looks like this. It has sample value equal to 1 here, 1 here, 1 here, everywhere on this side and on this side, okay, going all the way to minus infinity to infinity. This is a periodic sequence. And how often does it repeat itself? With every sample it repeats itself. So period n equal to 1. Okay. And easiest way is to sketch it. You can also substitute and verify that whether this particular expression is correct for all for all the values that we are looking at. Okay. So basically what we are saying is x2 of n is equal to x2 of n plus 1 for all values of n, which you can easily verify. Okay, now comes another interesting example of this type. This is the example number 3. x3 of n is equal to summation k equal to minus infinity to infinity, delta of n minus 4k. Okay, so easiest thing is to write down a few values, delta of n, that is for k equal to 0. Next term, delta of n minus 4 for k equal to 1, delta of n minus 8 and so on the positive side. On this side it will be delta of k equal to minus 1 will be n plus 4 plus delta of n plus 8 and so on. It goes on both sides. Okay, look at the sketch. There is a delta function at n equal to 0. Then there are 3 zero valued samples. There is a fourth one, that is, then there are 3 zero valued samples. Then there is another on both sides. Okay. Question, is it periodic? Periodic. Do you see something repeating from minus infinity to infinity? Yes. Periodic is yes. What is the period? What is the period with which it repeats itself? Period n will be equal to 4. Okay. So this is you know that this is a correct answer. Now tell me if this particular sequence is also periodic. Summation k equal to minus infinity to infinity, delta of n minus 4k. Same that what we saw in the previous one, minus delta of n minus 4k minus 1. Okay. Now, what is this function? This is the same as delta of n minus 4k shifted by 1 unit of time. Basically, it is shifted to the left or right. Shifted to the right, it is delayed by 1 unit of time, and a plus 1 became a minus 1. Okay. If the original function was periodic, shifting it by 1 unit of time will not change anything, so that will also be periodic. So what we say is this function is periodic, period equal to 4, period equal to 4. this is periodic, period equal to 4, okay. And if you go back and look at when you add two periodic functions, the value of n that you get, we said could be equal to p times n1 is equal to q times n2. This can also be written as the least common multiple of n1 comma n2, right? That's what this expression means. Okay, least common multiple of n1 and n2. Okay, so in this case you have n1 equal to 4, n2 equal to 4, least common multiple will be equal to 4. So is x4 of n periodic? You can say without even sketching it, you can say yes, it will be periodic. Why is it periodic? A sum of two periodic functions. Both of them have got equal period equal to 4. So therefore it will be periodic and it has to have period equal to n equal to 4. Okay, without even sketching. But of course, good idea to sketch. What does this function look like? It has a sample plus 1, then offset by 1 is a sample of minus 1, then 2 zeros, then you have a plus 1, a minus 1 followed by 2 zeros, a plus 1 and a minus 1 followed by 2 zeros and so on. So basically this is what will repeat from plus infinity to minus infinity. This is what it will happen. And of course this is a periodic function. It has period equal to 4, but you knew that even without sketching it by using the first principles. All right. So we have gained a lot of confidence in terms of looking at periodic sequences, upsampling, downsampling. A few simple calculations would also be helpful. So let me ask you to do a few more calculations.